I'd like to take another look at the theory involved with this sampling distribution material. Up until now, we've looked at the probability of selecting a case with a particular score from a population. For example, if I gave you the mean score on a particular SAT exam along with the standard deviation, you could tell me the probability of selecting a case from that population that had a score greater than 650. Let's just review that really quickly. Let's say we have a mean of 500 on the SAT. Let's say we know that the population standard deviation is 100 on the SAT. And we're looking to find the probability of getting a score X that's greater than 650. All right. Step one, of course, we need to draw this out so we know what we're doing. Here's my normal curve, and our mean is 500 on the axis of raw scores. But of course, we can't use those raw scores here because we need to refer to our z-distribution tables. We need to convert this to a z-score. So to do that, the next step is going to be just to remember what our z-score formula is. A particular score minus the population mean divided by the population standard deviation. So if I substitute in some numbers here, we're going to have 650 is the score that we're looking for. Oh, forgot something here, sorry. We are looking for scores greater than 650. We're looking for this area over here, and this is going to be 650. We'll just mark this out to know we have a z-distribution also. We can use the same horizontal scale to plot our z-score. 650 minus 500 divided by 100 is going to equal 150 over 100. And that is going to simplify out to 1.5. So that's our z-score. We would go to our z-table. I'm not going to do that here for you. I assume you can do that. And we'll just write out the probability that x is greater than 650. We're going to look that up on the z-table, and you'll find that this area over here, this area in here, that probability is 0.067, or if you prefer, 6.7% probability that we would select a case at random that had a score greater than 650 on the SAT. Okay. The probability of getting an individual score is not particularly useful. In sociology, in psychology, in all the social sciences, we're interested usually in comparing a sample of scores. We want to ask a question like, what's the probability that a sample of children who got, say, a new reading program scored better on a reading test than is typical? We're interested, in other words, in the probability of getting a particular sample mean. The problem is that samples, being samples, vary. Let's start off with a fresh sheet and consider a population of scores. Let's say that I have a set of scores where the values can be 1, 2, 3, 4, 5, or 6. This represents, in other words, a population. Let's say this is some kind of a test where people can score between 1 and 6. And let's say that one person scored 1, one person scored 2, one person scored 3, etc. We have capital N for the size of the population equal to 6. And we want to draw a sample from this population, small n. We use small n for a sample size. We want to draw a sample of 2. All right? And we're going to try to estimate, based on a sample of 2, what the mean of this population is. Now, we can look at this and you can compute it. In this case, you can compute it, and the mean is in fact 3.5 when we consider all the cases. 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6 is going to give you 3.6. All right. What if I draw a sample at random? We draw a sample with replacement. We draw a sample of a 2 and a 3. right? We've selected the child or the student that has a score of 2, and then we've selected the child that has a score of 3. We take the average of that, and we're going to get 2.5. Now, that's the sample we drew, but we also might have drawn a sample of, let's say, the student who got a 5, and then the next one we drew was the student who got a 6. In that case, the sample mean would be 5.5. All right. Remember, we're using these sample means to try to determine the true population mean, something which in the real world we really can't measure because it's just too expensive and difficult to reach everybody in an entire population. Let us in fact draw every possible sample that we could draw from this population of 6. We're going to get something that looks like this. This is every possible sample that I could draw. Now, important to remember here that I'm sampling with replacement. So, for example, in my 8th sample, this one over here, in my 8th sample, I've drawn the student who scored a 2. I've put him back into the population, and then I've drawn him again. So that's why I'm drawing 2 and 2. And you can see I could also draw, as I do here, a 5 and then another 5. Let's recap where we're at with this. We started out with a population. The population had 6 scores in it. The scores happened to be a 1, you could get a 2, a 3, a 4, a 5, or a 6. We can represent these in a frequency table that would look something like this. All right, and you can see the table. A value of 1 occurs once, a value of 2 occurs once, a value of 3 occurs once, etc. And to the right of that, you see a histogram. And the histogram in this case is showing what's called a uniform distribution. We've seen normal distributions, we've seen skewed distributions. This is an example of a uniform distribution. If you take a look at it, it very clearly represents what we're seeing in the frequency table. What I'd like to do now is show you a frequency table of our distribution of sample means. This represents the table from a few minutes ago that displayed the means of all possible n equals 2 samples we could draw from our population of 6 scores. You can see here that there were 2 samples with a mean of 1.5, 3 samples with a mean of 2, 6 samples where the mean was equal to the true population mean of 3.5, etc. Now the question is, why is this important? The key thing here is that regardless of the shape of the underlying distribution of scores, it could be skewed, that distribution could be bimodal, it could be trimodal, it could be uniform, as it is in this example here. If we take a large enough sample, though, from a population, again, regardless of the distribution of the underlying scores in that population, the shape of the sampling distribution will be normal. Okay, so why is that so important? It's important because we have the tools to determine the probability of events that are normally distributed. In this case, the event in question is the selection of a set of scores that have a particular mean. This property of sampling distributions forms the basis of just about everything we're going to cover in inferential statistics, and that's why it's critical that you understand it. Just as a final note, I would urge you to take a look at this website and run some simulations just to prove to yourself that regardless of the shape of the underlying population distribution, a sampling distribution created from that population distribution will always be normal or approach normal, assuming the sample size is large enough.